Welcome, everybody. It's my pleasure today to introduce Krystyna Kuperberg, and she'll be speaking on shape theory, Vietoris-Cech approach to homotopy.
Okay, thank you for the invitation. And I want to say that what I'm going to talk about is more history of shape theory, but the reason the approach that Borsuk chosen to étale homotopy is so popular right now is that it's very, very good, very applicable to flows, dynamics, and I suppose imaging as well. So, but there are other approaches, so-called pro-category, basically every compact space, Hausdorff, I suppose, would be described as an inverse limit of some inverse system of either polyhedra or NRs. And actually what Borsuk is doing is exactly that, but in a very, very special way. So, but my slides are not advancing.
No, even after we tested this. Oh, there you go.
Oh, I'm sorry, I had to click on the screen first. That's the abstract that I gave, so I'm going to skip that. So in 1927, Vietoris published a paper, very long, of course it was in German, and it was very difficult to read because Vietoris did not use a precise mathematical language. It was more descriptive. About the same time, Hurewicz published papers, which was very, very nicely written. So it was just the way probably Vietoris liked to write. And he described the Vietoris homology groups. They were just for metric spaces and compact. There are for metric compact spaces the same as Cech homology, of course. And he proved the Vietoris, what is known as Vietoris mapping theorem. And also at the very end of the paper, as I remember, he mentioned that he defined the first homotopy group, the fundamental group, using Lewis steps. And he just wrote one sentence, I believe, that this could be generalized to higher homotopy groups as well. But see, those Lewis steps, as you can see, is pretty messy. Much later, Christie did that. He was using Cech's nets, coverings, which is basically exactly the same thing as Vietoris does, because you can pick points there. And he also proved a new version of the Hurewicz theorem, which seems to have quite strong assumptions at that time. As far as I know, he did not do much more about that. So what Vietoris does, if you have this sin 1 over x circle, I just made it polyhedral, Vietoris would just make little steps around it to approximate it, just walk around it. And he defined for any compact metric space an abstract complex for every epsilon. Say he will have a complex. So epsilon simplex in dimension p is a finite set of points, of course, of p plus 1 points. And the whole set is of diameter less than epsilon. So he gets simplices. He gets the abstract complex. He gets the boundary operator, the chain complex. He has epsilon cycles, let's call them, epsilon chains, epsilon boundaries, and so on. So what is a little bit different than what he does, he actually considers two kinds of infinite chains. So infinite chain would be a sequence of epsilon n chains. When epsilon, the sequence epsilon, of course, approaches 0, it's called a majorant. I'm pretty sure Borsuk may have introduced this name. And so like those little steps around the sin 1 over x circle, and they are just approaching closer and closer. But for infinite change, say in one case, for epsilon 1, it can go once around the circle, and for epsilon 2 more times. So those are the infinite chains that actually don't give the groups. But for those, he defines a boundary in a very natural way, just the way it's usually defined. And then he considers some very special true cycles that they are just close to each other. So say if you want to go around the circle, you go around one time, the next one will be one time again, one time and approach. So they are homologous in some neighborhoods of the compact set. And I said neighborhoods because the one we had was embedded in the plane. So, but it was actually very easy to explain to students that for polyhedra, Vietoris homology was the same as a simplicial homology, because starting with simplices, you take the barycentric subdivision, and just the vertices that are introduced in successive barycentric subdivisions will give you those epsilon n chains. And you have chain homotopy, they are actually true chains this way. So somehow it was easier to explain that than singular homology. But also, if you start with the points and you don't have a polyhedron, but even an AR, you can extend to a singular chain, to a mapping. And for ANRs, you have the same thing as singular homology. However, what Borsuk did, well, we don't always have ANR, so let's just embed the space in an ANR and map those chains into that ANR. And they will be closer to the set. And that's when Borsuk started shape theory. So going back to that very simple example of the sin 1 over x curve, so that's Vietoris and that's Borsuk. That's how Vietoris approximate things, and that's how Borsuk approximate things. And originally, like in the mid-60s, 1960s, I was an undergraduate student there. Borsuk was trying to do a similar thing that Vietoris suggested, just using those epsilon simplices. So if you can just take a barycentric subdivisions or some triangulation of the spheres and map those vertices only into the space. And that was, as you can imagine, quite messy. So that approach seems simple, seems natural, and that's how Borsuk defined shape first. First, she just took subsets of the Hilbert cube, and he defined something that he called fundamental sequence, which actually is called shape map right now, from X to Y. So X to Y are two subsets, in this case, of the Hilbert cube. And you map X into neighborhoods of Y, closer and closer. So why do you need to embed X in the Hilbert cube? Well, because you want to have composition of maps. All those from X to Y, Y is in the Hilbert, the maps go into the neighborhoods of Y, and then from Y to Z again. So this way he could define composition of maps. And if you start with just a regular map, you can extend to the Hilbert cube both the range and the domain, and get so-called what he calls fundamental sequence. So notice in pro category, you would use just inverse, instead of neighborhoods, you would just use, say, polyhedra or ANRs. And is actually very much the same. If this, if it's embedded in some finite dimensional Euclidean space instead of Q, then the neighborhoods will be finite dimensional. Of course, nice finite dimensional ANRs you can get from it, and the intersection is inverse limit just as well. So there is really no real difference between Borsuk's approach and the pro-category approach or étale homotopy. But sometimes you have a thing in the plane. Why do we need the Hilbert cube? Also, sometimes you may like to consider things that are not compact. So instead of just taking the Hilbert cube, Borsuk took the Hilbert space, but you just take any absolute retract, not necessarily compact like the plane, and you define fundamental sequence from X to Y. X it can be in one ANR, Y in another ANR. The maps are from ANR to ANR or AR in this case, absolute retract. And again, composition is defined. And those are the shape maps. And they have to get closer and closer to each other. And that corresponds to those true cycles. But once you have that, you can take an ANR like the sphere and be mapping that closer and define very easily higher homotopy groups. And you can look at the homology this way. In Vietoris-Cech, homology and cohomology are what the homology and cohomology is in shape. So if you have two spaces and you have two shape maps, two fundamental sequences from X to Y and from Y to X, then you can define when the decomposition is equivalent to the identity map. So identity fundamental sequence will be the one generated by the identity map. And the two shape maps are shape homotopic if they are homotopic in smaller and smaller neighborhoods, those maps. So if both those compositions are shape homotopic to the identity, you have shape equivalence. In particular, if F is a map, is a shape equivalence, if such G exists, then those two compositions are shape homotopic to the identity maps. And of course, for ANRs, you just get the regular homotopy equivalence. So let's go back to those very simple examples. I said it's going to be simple. So a solenoid, this is two-adic solenoid as described as Van Danzig, but it's easy to draw in the plane. So it's not circle-like. That means it's not true that for every epsilon there is an epsilon map onto S1. I'm sorry, the solenoid is circle-like. This one is not circle-like because of the triad here. And but it's not the same shape of the circle. If you want to map circles closer and closer, you start to go around more and more times. And of course, in some neighborhoods, those will not be homotopic. However, this one is the same shape as the circle. You have approximate the circle, and then you can project it on the circle, getting the maps going both ways. And one of the notion that is very important is movable. Those belongs to so-called the UV properties. There are many UV properties very usable in shape as well as in flows. Oh, I misspelled and, sorry. So a compact set, this notion is Borsuk defined only for compacta, and it can be put in any ANR or AR. And for every neighborhood, there is a smaller neighborhood that can be pushed arbitrarily close to the set within the larger neighborhood. So you can move closer to it. And it's similar to the notion in flows, to the stability notion. That's why it was interesting. So this does not depend whether something is movable or not, does not depend on the ANR, does not depend on the embedding. And however, in dynamics, there are questions that are specific to some dimensions. So if something is movable in the plane, it's movable in the space. If it can be embedded in the plane, then it's easier to look at the plane. And it's that this is a shape invariant. So for planar continua are very simple. Continuum is, of course, a compact connected set. The shape depends on the number of the components of the complement. So if you have finitely many components of the complement, it's the shape of a bouquet of a finitely many circles. But other than that, it's really the same as a Hawaiian ring. So these two are shape equivalent. Also, Borsuk have shown that anything in the plane is movable. Well, it's the shape of this. This is very clearly movable. And Macmillan proved a little more general theorem that it's movable if it's embeddable in a surface. Another condition that is also very useful right now is called Mittag-Leffler, and this is Mittag-Leffler for first homology. And a compact set is Mittag-Leffler if for every large neighborhood there exists a smaller one, such that for anything smaller, these two images are equivalent. So of course that's not true for a solenoid because you wrap things around it more and more, so the images will be different. So, and if it's something is movable, that it is Mittag-Leffler. But again, instead of first homology, you can take other homology, you can have cohomology, you can do some other stuff similar. Well, cohomology is a little bit different, but clearly the one can be replaced with something else. So solenoids are not movable and they are not Mittag-Leffler. There is a continuum called Case-Chamberlain, which has the property that there is no essential map onto a circle, but there is an essential map on a one-point union of two circles. And it is an inverse limit with the same map all the time. A and B are those two generators in the wedge of the circles, and you just go around one loop, another loop, and you go back. And Mordeshitz has a really nice paper classifying those, I think, and also he shows that the suspension, the topological suspensions, the union of two cones, is movable. Now in dynamics, the Denjoul continuum is movable. So what is Denjoul? Probably everybody knows, but let me mention what the property of it. It's something that is embedded in the surface of a torus. Locally is the Cartesian product of the Cantor set and the interval. And every R component is dense. So it's almost like a solenoid, but it's not a solenoid. No, this was used for some counter examples in dynamics in a very important way. And it is movable because it's in a surface. Now I wanted to also say there are two definitions of basic for movable, for compactum and sort of pointed movable, which I didn't put on the slide. Pointed movable is that you just keep the point X naught, chosen point, like the base point for homotopy, always in the same place. And it's still an open question whether something that is movable is pointed movable. It's, as far as I know, it's still a very open question. Then Borsuk defines something approximately and connected. If for every neighborhood there is a smaller neighborhood such that every map into the smaller neighborhood is null homotopy in the large one. That corresponds to the infinite cycle in Vietoris homology being homologous to 0. So I'm almost at the end of what I'm talking about, so I will probably finish earlier. So I probably should have added a little bit more to this talk. So let me just say that one of the theorems proved by Christie was Hurewicz theorem using nets. And I had a version of it as still a student in Warsaw. And so for n equal 1, you have the first homotopy group, and there is a theorem similar to that. The first homology group with z coefficients is the first homotopy groups abelianized. That's for path connected spaces. So you have the notion of approximate n connected, but you have also the notion of Vietoris path. So for homotopy on path connected here, connected is not enough. So you take the solenoid, you take 2 points in different components, in different arc components of a solenoid, and attach to one a circle and to the other, say like S2. So you will have different homotopy groups at the point where the circle is attached and different homotopy groups at the other one. And the points where nothing is attached, they will be just all trivial. So Vietoris, I'm not sure he actually did that, but it was very natural to do that sort of Vietoris path. You have a sequence, you have 2 points in a continuum that is embedded in some nice ANR, and you take paths in the ANR, joining the 2 points that are getting closer and closer to each other. So that's the Vietoris path. So if you want to consider anything like the Hurewicz theorem, the connection between the homotopy groups and the homology groups in Vietoris sense, so the homotopy groups in shape sense and Vietoris homology, then you probably want to have this Vietoris path between any 2 points instead of just saying path connected, which is a little bit too strong. So for example, if you take a solenoid and attach a circle to at one point, at that point, the first homotopy is going to be Z. First homology with Z coefficient is going to be Z, but another point, that's just going to be, the Hurewicz theorem would be false. So that's the natural assumption. So the theorem says that if the space is approximately Q connected for any Q between 0 and n-1, 0 just gives you basically, for one, take path connectedness, and then for 1 gives you those Vietoris path between points. But if it's all the groups, although it's approximately Q connected, then in dimension n, these two groups are isomorphic. So when you look at the étale homotopy and they just say, well, some sequence of groups is trivial, if you look at exactly at the definition, which you usually have to go much back, that turns out that that's the assumption also. So a stronger version of the shape version of Hurewicz theorem, when you just assume that the groups, shape homotopy groups in Q dimension are trivial, that's false, even for spaces that are path connected. So I look at that, the homotopy group of spheres. As you know, they are funny. And the forthcoming homotopy group of S3 is Z2. So if we take a three-adic solenoid, or could be some other adic, but not two-adic, some odd number. So let's take the double suspension that's going to give you something like S3, but solenoid or S3. And for that space, the first groups from 0 to 3, I mean, it's path connected. So they are trivial. The fourth Vietoris homology group is trivial, of course, but the fourth homotopy group in Borsuk sense is not trivial. And because of that property. So if you take an essential map from S4 onto S3, and you take this wrapping 3 times, it actually is 16 rod squares, it multiplied by 9, that's modulo, that's also a non-trivial map. And that kind of shows that the homotopy groups are not stable in that sense. And as far as I know, it's the only example, but one can construct, for other spheres as well. So,
can I ask a question here?
Yeah.
So you're using sort of a non-trivial map from the 4-sphere to the 3-sphere.
Yeah.
Right? Why couldn't you do this construction with a non-trivial map from the 3-sphere to the 2-sphere?
Because that homotopy group is Z.
I see.
And you want to have something modulo something.
Okay.
So if you wrap it so many times, you get back to the generator.
Gotcha. Thank you.
So, but that's actually a very interesting question, because there is an interesting example. When you take this S1 cross S1, a surface of a torus, and you have the 2 generators, and you take a suspension of a 2-adic solenoid, so you have something like S2, right? And you take a circle in it that goes all around from the south pole all around, but through points in different components. So you do have the circle, and you glue it to kill the 2 generators. You take 2 copies, you kill 1 generator and another generator. If you kill it with a disk, you get something that has this, that is the same homotopy type as S2. If you do that, you get something very strange. But this, even if you kill it with something so strange, one won't work to make the second homotopy group non-trivial, but 2 do. 2 of those do. So you can jump from one to the other with the approximations. So those suspensions of solenoids are a little bit tricky. Yeah, I'm not sure if that was interesting. And that, just to look at the suspensions of solenoids, how they can be used, they are a little tricky. Okay, so as I said, I was didn't prepare enough material, and I finished a little bit early. So if you have any questions, if anybody has any questions, the other theorems that I sort of wanted to talk about but gave up on were Vietoris theorems. But let me just make one comment on it, because there is Vietoris-Begle theorem. So the first Begle theorem was for Vietoris map, was exactly what Vietoris did, except he used Cech homology, that means non-metric spaces. His second was just for group coefficient that was compact, and for if the group of coefficient is compact, then the Vietoris theorems work fine, just assuming instead of infinite cycles disappearing, just true cycles disappearing. So, but for that, there was some confusion that Vietoris might have had a mistake. That's absolutely not true. He was considering acyclic in the sense that the infinite cycles were homologous to 0 of the right things. That means the pre-images of points. In shape theory, of course, you don't have pre-images of points. You have to do it a little bit more general, but everything seems to work just fine. All those classical theorems have some version in shape theory, and somehow it was, sometimes was easier to look at pro groups. Sometimes it was actually nicer to look at something that you have in the Euclidean space. And for applications, like deciding what something looks like, it's easier to look at objects in the space. For instance, the pseudo-circle. Well, it has the same shape as the circle, but fortunately it was defined in a very messy way. Nobody even knew how many of those there were. And it's planar, so it's movable, but it was important that it could be embedded in a plane. You could actually see it in a way. Okay, so that's the end. That's the end.
Great. Well, before we get to questions, let's briefly unmute ourselves and applaud for the speaker. So any public questions for Krystyna? Let me start. I was hoping you could walk me through the definition of Vietoris-Type homology to make sure I understand it. So this was near the beginning of your talk, if you don't mind going to those slides.
Okay, I'm going back to the slides. Which slide do you want?
It's probably slide 2 or 3. I'll let you.
So you want the definition of shape map?
No, of Vietoris homology. So yeah, so right here. Okay, so so we have a sequence of chains, and each is an epsilon n chain where epsilon n is going to 0. And then, so I see that's the definition of an infinite chain. And then it's a cycle if its boundary is 0. So that just means the boundary of each gamma I.
Yeah.
And then.
So you have so-called abstract complex. And really, if you start with a polyhedron and you take the barycentric subdivision, this is like a good model for those chains.
Meaning I start just with any, sort of collection of edges, say, and then as I subdivide, they keep getting smaller and smaller.
You start with some triangulation and you do have vertices, and you can tell which subsets of vertices are simplices. So that's the abstract complex. But then you take a barycentric subdivision, you get more vertices.
Right.
And you have, but also you can tell which one are simplices or not. And they are smaller and smaller, right?
Right. And so I understand also what it means for an infinite cycle to be a boundary, that you have a sequence of boundaries essentially. And then, so I haven't yet understood the definition of a true cycle. So
true cycle, see, okay, this could be written differently. You have an infinite cycle, gamma sub 1, gamma sub 2, and so on. But then you take another infinite cycle from this one, starting with gamma 2.
Right.
So you shift it.
So you want all the steps to be homologous to each other.
So you want those to be homologous, but actually, starting from some place, given the neighborhoods, if you say now starting from some place, they will be all homologous to each other in the neighborhood. If you look at this as singular homology.
Right.
So here you have, there will be all homologous with, the closer you get, the smaller the simplest are, but not just in that true cycle, but also in the cycle of dimension 1 higher, in the chain of dimension 1 higher, whose boundary you take, right?
I see. So you're saying in nice spaces, these cycles eventually always have this property of the
So if we take something like circular, like the sine 1 over the x circle, which incidentally is called Polish circle in Austin, and in Poland it's called Austin circle because of some arguments between Borsuk and Bing.
in Poland, it's called the what circle?
Austin.
Austin. Okay.
Yeah. It was called Warsaw circle by Bing and Austin circle by Borsuk.
Oh, Austin as in Austin, Texas, where
Like
Bing
Austin,
was.
Texas, yeah.
Oh, wow. Oh, great. That's fantastic.
As we were told by Borsuk, so I'm not sure that was true. Because Bing called it Warsaw circle, and there are two versions. One is one you have this little triad, and the other just connect the bottom. So the other one is actually circle-like. But Bing liked to give names to everything, right? So it was sort of like a payback. But I'm not actually sure that history is right. I'm actually not sure.
And then do you mind going to the next slide as well?
Oh, I need to.
There we go. Okay, I see. And so
okay, so if you want to get through cycle here, the first few steps don't matter. So you have those epsilon steps, right?
Mm-hmm.
With the next one, if you go here around once, with the next one, you want to go around once as well. Okay?
Right.
Because if some neighborhood that is like an annulus around, if you go around a different number of times, they won't be homologous.
Right.
You cannot get this chain with those small triangles. So the difference will be a boundary, sort of like an annulus. And same here in Borsuk version, if you want to form a shape map, and here we go around once, next one you will go closer to it, so you will make more wiggles, but also you go around one time.
And so is it correct to say that that Vietoris homology, you're looking at, true cycles mod boundary?
Yeah.
Given the definition of true cycles you just gave, is that right?
For homology groups, you want to have those true cycles. So the first homology group of a solenoid with Z coefficients is trivial, because you don't really have any true cycles that will go around the same number of times, but getting closer and closer.
Right.
However, for some of his theorems, like Vietoris' theorem, he does not only assume that the true cycles vanish, but the infinite cycles
I see.
Vanish as well. So
so he considers both for different purposes.
So say if you take a solenoid, two-adic, and one point in one arc component and another, and you join them with an arc. So then you take a map of a circle contracting the solenoid to a point. This would not be so-called Vietoris map, although the inverse image of every point has trivial homology with Z coefficients. Okay, so the question was, is that acyclic? What does it mean acyclic? What kind of groups disappear, right? And that causes sometimes some misunderstandings. But only occasionally. But one of the big things is Vietoris somehow had a mistake, because it's not true for Z coefficients if you assume that only the infinite, only the true cycles in the pre-images of points disappear. You have to have something a little bit stronger, which Vietoris does have. But Begle had just two versions, one with groups like Z coefficients, and the other with coefficients the coefficient group would be a compact group. And for a compact group, then you assume would be enough only to assume that the groups disappear. They are cycling in the sense that the homologic groups with those coefficients are trivial. And then you get up to a certain dimension, and in that dimension you get isomorphism. In dimension higher, you get epimorphism. So I think epimorphism, and if I remember correctly, but that's kind of very easy to construct that. So in homotopy, shape homotopy, instead of saying the infinite cycles disappear, we have this approximately, which a word that people don't like, but that's what Borsuk is, approximatively, and Q connected to a certain dimension, right? Which corresponds to the infinite cycles disappearing. But it's very natural. So if spaces are movable, those two notions, whether infinite cycles disappear or true cycles, are equivalent. So the version of, for example, Hurewicz theorem for movable spaces is easier. It's just the groups disappear up to the dimension n-1, then you have an isomorphism in dimension 1, in dimension n.
Thank you. So more questions from folks? Well, if not, thanks so much, Krystyna. It's really important to be, keep learning more about this history. So we greatly appreciate it. So let me stop the recording here. Thanks so much.